Hello everyone, and welcome to another episode of the Dorky Dunkleosteus. Today we're going back to Geology 101, and we're going to be discussing what is a mineral. And I'm going to apologize ahead of time, because mineralogy is not my forte, and it gives me a headache. So, let's make some important distinctions first. It is important to know that definitions can differ between commonly known definitions and scientific definitions, and different scientific disciplines. Scientists use specific words and definitions because it helps us build a framework that can be used across the globe in the scientific community. So there's very specific words that are used in each definition, and those definitions are universal only in that specific discipline. We're going to be seeing a lot of cross-discipline definitions, but most of them are either brought from chemistry into geology or are strictly geology. What is a mineral? A mineral is defined as a solid, inorganic substance of natural occurrence according to the Webster Dictionary. So this is basically what layman's terms is a mineral. And not talking about like mineral water or anything about that. More scientific, but still layman's terms. Geologists define it a little differently. We get a lot more specific. Geologically speaking, a mineral is a naturally occurring inorganic solid crystalline substance that has a chemical composition which is either fixed or which may vary within certain defined limits. So those words you'll see are italicized and bold. That's because most of them I'm going to define right now. The solid. So a solid is one of the major states of matter on planet Earth, a stable, rigid state of matter that has defined volume. So this comes from chemistry. So we're looking at a solid being that atoms and molecules in the atomic structure have stopped moving, at least to a point that we consider them no longer moving. We're not talking about absolute zero or anything like that, because that's a theoretical zero. We've gotten close. We haven't gotten to absolute zero yet. So it's solid, so the atoms are not bouncing around all over the place. They're very tightly packed, and they have a definite volume. Inorganic, something which has never been alive or part of something that was alive. So this is something that definitely confuses me sometimes, because there is such a thing as organic and inorganic carbon. And that can cause some problems because, I'm not a mineralogist, I'm a geologist. Because it's kind of hard to tell which carbon you're dealing with. At least when I was in school, it was pretty hard to tell what I was dealing with when it came to inorganic or organic carbon. But we didn't touch about that. That's something for, doctoral degrees and stuff. So, carbon's one of those things that we just kind of put on a pedestal and go, we're not going to deal with you unless we absolutely have to. So, what's some great examples of inorganic things? Elements. Most elements are actually inorganic. So, gold, copper, oxygen, these kind of things are inorganic. Says they were never alive, or they were never a part of something alive. Quartz is another one. It's SiO2. It's a specific molecule. And then copper wire. This stuff was never alive and never part of something alive. So, naturally occurring. This means something that happens naturally without any outside human forces. Basically, if human hands have helped shape it, it is no longer considered naturally occurring. So there are some elements that can only be created in human laboratories. Those elements, then, are not naturally occurring. And then we have other stuff that's for like phones, cups, pots, that kind of stuff. That's inorganic, that can be organic, but it's not naturally occurring. Naturally occurring, you're looking at gold, again, you're looking at rocks, plants, this kind of stuff that has not generally been shaped or formed by human hands or technology. crystalline. This is difficult because we're looking at crystal lattice. A material having an atomic structure which form a fixed crystalline structure or crystal lattice. I do have a picture here of crystal lattice examples, and this is all basically how the atoms and molecules in the chemical formula, which we'll talk about next, arrange themselves in a solid form. There's a hexagonal, there's cubic, there's a whole bunch of others, and it's pretty complicated. Chemical composition. This is the recipe that makes up a mineral or a compound. So, like I said earlier, quartz is SiO2. That's silicon dioxide. So that is its recipe. You are not going to find quartz with any other base chemical compound. It will not be quartz if it's not SiO2. But you will see what are called trace elements in quartz. That's how you get rose quartz. That's how you get amethyst. That's how you get all of these different colors. Simply because trace elements get stuck in the crystal lattice, and then those elements actually transform the color. It either interacts with light somehow, or it interacts somehow with either the spaces or voids between atoms, and creates something that is chemically the same, but those trace elements differ it enough to be something unique. So, technically speaking, anything that has a trace element in it still is its, still quartz is quartz is quartz is quartz. Doesn't matter if it's amethyst, it's quartz. It's just purple quartz. The reason it's purple is the trace elements. So we gave it a special name. Rose quartz is just quartz with pink in it. And by pink, I mean the trace elements make it pink. And there's a whole bunch of other stuff. That's just quartz. There's a whole bunch of other stuff. So the recipe consisting of distinct elements or compounds in a specific arrangement at the atomic level. So yes, a lot of what we're going to be talking about with mineralogy is going to be at the atomic level or a little bigger. It's going to be atomic level or macro level, which is basically hand samples. Most of it, though, is atomic. What is considered a mineral? Geologically speaking, there are a lot of minerals. A lot. There's different types. So we have silicates, sulfates, carbonates, oxides, halides, sulfates, phosphates, and natural elements. Just to let you know, the largest of these groups is actually the silicates. That is because Earth is a silicon-based planet. So, yeah, pretty complicated. Some minerals are quartz, feldspar, calcite, corundum, also known as ruby. It is pretty diverse. Basically, if you go into any gem and mineral collection at a museum, if you look at any of the gems, you're generally going to be looking at pure minerals. With some exceptions, especially if it's man-made, but that's generally what you're going to be looking at. So, what isn't a mineral? It's easier to say what isn't a mineral. It's anything organic or man-made, anything that doesn't have a definite crystal structure, and anything not a solid. So man-made diamonds or gemstones are not considered minerals because they are man-made. Glass, volcanic or otherwise. So if it's glass, it has it's silicon, it's sand, so it's generally SiO2. It's solid, but it does not have a definite crystal structure. Glass is actually what we consider frozen quartz from magma. So that is why we don't consider obsidian a mineral. It is a mineraloid. It almost is, but it doesn't technically classify. And natural glass, yeah, that's not technically a mineral. Water. If it is either a vapor or a liquid. If it is in its solid form, so if you have ice, ice is technically a mineral because it's inorganic, so it's H2O. It has a very definite crystal structure when it is in the form of ice, when it's solid, and it's a solid. So that checks off pretty much the three main biggest things that make it a mineral. So that's pretty cool. Mineralogy is its own beast. It's a very specific focus in geology, and it actually has so much going on. It's really, really complicated, and it makes my head hurt trying to think about it. This was the hardest thing for me in my degree to grasp and get my head around. I still passed it. I still did a very good job for me. But I had to work really hard at it because mineralogy is very, very specific. It is very, very difficult when you're getting into the nitty-gritty and the details. But mineralogy is still good to learn the basics at in an introductory course. So this is pretty much what you're going to be learning in any kind of Geology 101. Introduction is this right here, which is how to identify a specific mineral. It's a test. That's what it is. There are multiple properties. When you add them all together, you will be getting a unique mineral. Now, some of these are less common, and some of these are more common to use. The very first one, crystal structure and habit, is pretty hard. You would be looking at something on the atomic level. So generally, that's not going to be something you can field test. The rest, generally, you can figure out in the fields with either no tools, simple tools, or, really, really easy things to get, or you can buy. So hardness, it's a scale of 1 to 10. 1 is talc, 10 is a diamond. Everybody, even in high school, in their introductory science courses, probably remembers doing these hardness tests. And you can actually figure out the hardness pretty easy. If it's greater than a 3, you will not be able to scratch it with your fingernail. If you can scratch it with your fingernail, you're looking at a 1, a 2, or a 3. So it's going to be talc, or the other two. There's still a list there. If you have a nail is generally about a 7. If you have a piece of glass, that's 7. The one thing I will say, they say that only a diamond will scratch glass. That is not true. Glass is a 7. A 7 can scratch another 7. They will both be damaged. So if you take quartz, which is basically the mineral of glass, and scratch it against glass, you will leave a cut. You will damage both the glass and the quartz. If you take a ruby and you scratch glass, it will not be damaged, but it will leave a much deeper scratch on the glass. So, basically, if you're trying to see if something is a diamond, you're going to want to scratch it on corundum, which is a ruby. And you really don't want to do that because that's going to scratch the ruby if it's an actual diamond. Or if it's not a diamond, it'll just be glass or some kind of other man-made, another man-made type of gem. You're gonna basically just scratch that. So, just a memo there. Luster. Okay, is it shiny? Is it metallic? Is it waxy? Is it pearlescent? So there's a bunch of different ways that we describe luster. Luster is when the light hits it. This is how I think of it. When the light hits it, what does it look like? I have pyrite. Pyrite is very metallic because when you shine it, it looks like fool's gold. It looks like gold. I have some silver that also has a metallic shine to it. When I look at something like a piece of quartz, that's glassy. It doesn't have that shine. There's certain other gems and other minerals that will be waxy in appearance and even in texture. Pearlescent, does it have that oil slick look in the light? Really kind of cool. Color and streak. What color is it? What color does it leave when you scratch it on a ceramic plate? An unglazed ceramic plate, mind you. So color is going to be the very first thing you're going to notice. You cannot rely on color alone because there's a lot of minerals that have the same color. The streak is something that you can use really easily. So if you're ever going out digging or doing mineral, definitely have a little sample tile of an unsealed ceramic. Definitely white. You want it white. And that will be your scratch plate, your streak plate, because then you'll be able to just quickly scratch the plate with the mineral and it'll leave a different color. Gold, if it's real gold and you scratch it against that, it will leave a gold color on the streak. If you have fool's gold, you scratch it, it will leave a black color. So that immediately, if it looks like gold, it's got that same kind of shine to it and everything, but you scratch it and it's black, that's pyrite, iron. That's iron pyrite. Cleavage and fracture. And no, I'm not talking about boobs or broken bones. So the minerals have something called cleavage. And that is how it wants to break cleanly. That is how the planes in its atomic structure are arranged to be the weakest point, and it will break. Cleavage is going to be kind of hard to be out in the field, but sometimes you'll get lucky. Especially if you have a piece of quartz, you'll be able to see the internal cleavage structure. Generally, cleavage also will form your planes or your terminations. So you will see, if you have a really, really good quartz crystal, it will be hexagonal, so it'll be six-sided with a pinnacle on top. If you weren't sure, you could just look at the cleavage itself, because it will not, if you break it along its cleavage, if it's clear, you'd be able to see probably micro breaks in there, and you'd see these internal planes breaking in the exact same structure. Generally, if you just gently crack a quartz crystal, most of the time it's going to split carefully along the plane, but how it fractures, which means how it actually breaks under a lot of stress, is how you'll also know. A fracture is basically if you take a quartz crystal and you really smash it, and you just really, really put a lot of force behind it and you smash it, you will see what are called conchoidal fractures. That looks like when glass breaks. A large chunk of glass, when it breaks, it will have this weird kind of, I don't even know how to describe it, and I'm not having my camera on today because I don't want to deal with the camera today. And I think it runs everything down. But it gives this kind of half moon shape, glistening. It's weird. If you've ever broken a glass plate, you'll know what I mean when you look at that broken edge. It's really specific, and how a mineral sample fractures will define how it, what kind of mineral it is. Specific gravity. So this is its density of the specimen. This is something that you can figure out pretty well. There's cheap little, well, I wouldn't say cheap. They're, a little more expensive, but you don't have to get a really high-tech gravity, any kind of machinery. There are plates that you can get that are basically like scales, digital scales, that they will have specific gravity or density on there. And you can use that. It's pretty easy. Specific gravity, again, you're not going to use it too much in the field, because you won't need to be very specific. For me personally, if I pick up something that looks like it's small and hand size and should be really light, but it's really, really heavy, I know the chances are it's probably got iron or lead in it. I would then do more tests to figure out, okay, what is this exactly? Basically, it's your density. A lot of times, you're not going to be into the specifics of it. You'll be able to feel it. It's like, okay, this is a higher density. This is definitely heavier than it looks. that's already got in my mind a couple different ideas. Other properties. So some minerals, very rarely, but they're very, very specific, will have very, very unique other properties. An example, fresh sulfur. Mineral sulfur smells like rotten eggs, and it reeks. It really does. And if it's red, if you're not sure, and you scratch it, because it's bright yellow, but if it's been sitting out, that smell kind of degrades and it kind of just becomes rock. But if you scratch it and you smell rotten eggs, that's sulfur. You don't need to do any other testing. Salt. If you are not sure if it is salt, I do not recommend this as as the first thing you do. Other than the fact that salt will form perfect cubes, and it has perfect cleavage, it's salty. But what else can I say? Sometimes calcite can look like salt if you're not too careful. But yeah, I wouldn't use taste. Because you can potentially ingest some very noxious, poisonous, potentially life-threatening, minerals out there. Like elemental arsenic. Yeah, that's not fun. But generally, I would say for salt, you need to be very, very sure. Not saying there's a lot else out there that can look like salt, but don't go to taste as your first option. That's all I'm saying. There's some other things as well, but you learn that as you learn. And honestly, a lot of times you will figure them out right away. You'll start to get your specialties. You'll start to realize really quickly how you can identify quartz, how you can identify calcite, two of the most common minerals you will ever see, besides salt. You'll find a lot of different tricks and trades, and I will tell you this, no geologist that I know that works out in the field has to go through every single one of these tests to figure something out, because we all have our shortcuts, and we all should know the geology of the area that we're working in. And if you know the geology, you know what minerals you're generally going to run into. So, kind of some hints and tips. So, important things to know. For me, these are the basic things you need to know. The hardness, great way to test in the field. Luster, it's all visual. It may be a little more difficult, let's say if you're slightly colorblind, but luster is more useful than color, in my mind, because color is very subjective, and especially if you're colorblind, but also a lot of minerals have the same color. Fracture. Yeah, most often you're not going to find a perfect crystal. You need to know how it breaks, and what it looks like when it breaks, because that's generally when you're going to find it. And chemical formulas. You're going to learn a lot of chemistry if you continue on with geology. But you're going to be learning a very specific type of chemistry. You're going to be learning geologic chemistry. And it's a different monster. Chemistry was difficult for me. But when I looked into geologic chemistry, geochemistry, it's a different thing, because you're dealing with something that you generally will start to understand, because you're not dealing with organics. You're not dealing with, lipids and fats and all that kind of stuff. You don't have to deal with that. And that's a majority of organic chemistry is. General chemistry, it deals a little bit more with the lipids and everything, but geologic chemistry I actually did enjoy when I had those labs. You're going to learn SiO2 is quartz. You'll know feldspars. They're also some of the most common minerals to find. I can hear in my head my geology professor yelling at me, and my mineralogy professor yelling at me, because there was a formula he drilled into our heads and I kind of didn't really remember it very well, and I cannot tell you at all what mineral it was or what the formula was. I completely forgotten it. I'm sorry, Dr. Solar, forgive me. I have committed the geologic sin, the mineralogy sin. I've forgotten that chemical formula. But that's just because I don't deal with, at least in my day-to-day life and in my professional life, I'm not dealing with chemical formulas, but I do know quite a bit because I work mostly in areas that are mostly silica-based. So, that's pretty much it. I don't think... okay, in conclusion, yep, there's a reason why mineralogy is a full semester course on its own in college, in a bachelor degree. It's a monster. You'll learn a lot, though, and you'll learn a lot of shortcuts that are going to make everything a little easier for you. And honestly, it's fun. It's very, very fun. It's a lot, but again, like I said, I had to put a lot of work in it, but I did learn a lot. It's important in geology to know this. Even if you just know the basics, it'll take you a long way. Next episode of Geology 101, we will go back to some easier things. We'll talk something a little less atomic and cerebral. We'll talk something a little easier, something a little bit more on outside of bachelor and back into that intro class. So I forgot to put a sources page on this. Honestly, a lot of times I was just looking through my notes on this and then pulled up some images on Google. I did use Merriam-Webster, and of course I used Wikipedia. I love Wikipedia. So thank you again, everyone, for joining me on another Geology 101. I am going to try to continue doing episodes every week. I'm hoping that this lovely thing called the quarantine is going to be lifted soon, but I'd rather be safe than sorry. I'd rather look back and say, maybe we were over-prepared, but I'd rather be over-prepared than under-prepared. Leave a comment, leave a like, ring-ling-ding-ding-ding that bell, subscribe. Let me know you're enjoying these. I enjoy doing them. I enjoy sharing my knowledge. I enjoy sharing my passion. So happy to have you guys here again. I will see you next week. Remember to stay safe, stay smart, and to keep on digging, everybody. Thank you so much, and have a great one. Bye-bye.